We're going to wrap up Note 16 by looking at how we can put these confidence intervals together into one sort of cohesive thought as a whole. So in the ANOVA F-test that we did back in Notes 15, we had a really small p-value. And this indicated to us that the population mean number of cases sold was not the same for all four package designs. What we want to do with our simultaneous confidence intervals is to take that a step further and say, okay, well, which package designs do we think have different population means? And if you look back up here, you'll see that these ones with stars are the intervals that do not contain 0. So these are cases where we think the two package designs have different population means. And it looks like we think that 4 and 3 are different. We think 4 and 1 are different. And we think 4 and 2 are different. So there's 3 more sets of stars here, but that's just 3 and 4, 1 and 4, and 2 and 4. So remember that everything's on here twice, just repeated. All right, so that tells us that we think that all of these designs, or these pairs, have different population means than one another. That's going to get us started, but what we really want to know, what the cereal company wants to know anyway, is one package a clear winner? Like, is there one design that they should really use if they want to increase the population mean sales? So looking up at this, if there's going to be a clear winner, it looks like it's got to be design 4, because I think 4 is different from 2, I think 4 is different from 3, and I think 4 is different from 1. All right, so clearly 4 sort of stands out in some way. Now, if I go back up to my list of intervals, all of these intervals where I compare package design 4 minus the population mean for one of the other package designs, these are all entirely positive. And what we said is that if this is an interval for mu4 minus mu something else, and the entire interval is positive, I can be confident that package design 4 actually has a higher population mean than the one that I'm comparing it to. So what we can do by putting all of these together is we can say that design 4 looks like a clear winner. In every case where we compared design 4 to another design, we came away confident that the population mean was bigger for design 4. And this is the part where we finally see why it's important that we made that Bonferroni's method correction earlier. Basically the idea that we made our individual intervals higher than 95% confident. Because at this point, because these are simultaneous 95% confidence intervals, I can be 95% confident that design 4 has the highest population mean sales of my 4 designs. If I hadn't used Bonferroni's method, if instead I had just made 6 different 95% intervals, my overall confidence would be a lot lower than 95%. And if I tried to go to the company that made the cereal and say, I made 6 95% intervals, I think design 4 is the best, I might only be something like 70% confident when I told them that. Because I used Bonferroni's method, I can be 95% confident that design 4 has the highest population mean sales. So this is a really important thing to do, and it's something that people forget about sometimes or don't know about. And so if you're in another class or doing research for one of your majors or something like that in the future, and you find that you're doing a bunch of different hypothesis tests or a bunch of different confidence intervals, remember that this is a way that you can make sure that your overall confidence is still high, even if you're doing, say, 6 different confidence intervals. So we answered one important question. Is there a clear winner in terms of population mean sales? We might also wonder if there's a clear loser. Is there one package design that's clearly worse than the others? And this is the place where it gets a little more nuanced, maybe, where we could clearly say that design 4 seemed different than design 2, seemed different than 3, and it seemed different than 1. Well, design 4 was the clear winner. But when we only compare 1, 2, and 3, it seems like we're actually not sure if any of them have higher or lower population means than another. Because if I compare, say, 1 to 3, my interval contains positive and negative numbers. If I compare 1 to 2, it contains positive and negative numbers. And if I compare 2 to 3, it contains positive and negative numbers. So for each of those comparisons, I'm not confident that either design has a higher population mean than the other. So it looks like there isn't actually a clear loser. Every other comparison I try to make, I don't really come away saying, yeah, this design I'm confident is better than the other. So the reason that I'm pointing this out is that sometimes there is a clear winner. Sometimes there's a clear loser. Sometimes you don't get either one of these. And so you want to be careful that you are checking the different combinations and being a little bit careful about this. All right? One other thing that I want to point out, or maybe two other things here before we wrap up this section of notes. We were simultaneously 95% confident in our intervals. We could do this for 90% simultaneous confidence, 99%, whatever it was that we wanted. If you add alpha equals 0.1 to the end of your first line of code, so if you go back up here and right after data equals stores, if I put alpha equals 0.1, this is how we changed our confidence level in the past. And what you'll see is that that changes your simultaneous confidence level when you add this means line or this ls means line. And so I would go down and I would see that now it said that I was 90% simultaneously confident. All right? And if you do that, what we've seen in the past is that if we don't need to be quite as confident, our intervals can actually be a little bit smaller, right? Because if we're imagining our intervals to be a net, we don't need as big of a net if we're only going to catch the thing 90% of the time as we would if we wanted to catch it 95% of the time. And so when your intervals get a little bit narrower, you might find that there's some comparisons that had positive and negative numbers originally and now only have positive or only have negative. And so when you do this, you'll see that if you only need to be 90% confident, we can actually add in at that point that we're 90% confident that design 2 and design 3 also have different population means. So try this for yourself. Let me know if you have questions or anything on it. And then I mentioned there were actually two things here. The other thing that I just want to point out, Bonferroni's method is one way for giving us this overall confidence or creating what we call simultaneous confidence intervals. That's the method we're going to use in this class. It's a very common method that a lot of other disciplines and things use. But I just wanted to let you know that there are other methods. So if you replace where it said BON in the code and write Tukey, it's named for John Tukey, who was a statistician. He invented the box plot as well as several other things that we've seen this semester. You'll notice that you get slightly different intervals because it's using a slightly different method. All right. So the very last thing that I want to mention is the main takeaway from this section. We talked about this earlier in the notes, but if you really only remember one thing from this section of notes, the important thing to remember is if you want to be, say, 95% confident, and you're going to make a bunch of different confidence intervals at once, you need to increase the level of confidence for the individual intervals to have that overall confidence that you want. That's the really important part. So again, if you're in another class, if you're doing research in your field or something like that, and you're going to make a bunch of confidence intervals to make some sorts of comparisons, if you want to be 95% confident in all of your comparisons, your individual intervals need to have a higher level of confidence. And Bonferroni's method is one convenient way of doing that.